Good morning. Thank you all for joining us. Welcome to our June Global Resilience Commission webinar, The Black Sky Chaos Problem, Recovering from Armageddon, where we will focus on complex interactions and interdependencies of infrastructures and other systems that we rely upon, and try to find both solutions and advantages in those systems. I'll be joined, my name is Dr. Chris Beck, and I'm the Vice President for Policy and Chief Scientist at EIS Council, and I'm very happy to be joined by my colleague, Dr. Anthony Bucci, who's the Technical Director for Infrastructure Simulation at EIS Council. Anthony leads the modeling and simulation initiatives, and in particular, he is the technical lead and developer of the Global Infrastructure Network Optimization Model, or Genome, our large-scale multi-sector meta-simulation. And he'll be giving us a brief overview of that in a few minutes, right after opening remarks from our CEO, Avi Schnur. He's the founder and CEO of EIS Council and has defined EIS's mission focus on severe black sky hazards to lifeline utilities, corporations, and governments worldwide. We're happy to be joined by a panel of distinguished experts. Saskia Sardazai is a senior scientist at the Fraunhofer Institute for Material Flow and Logistics. She conducts integrated logistics research in all fields of internal and external logistics. Dr. Wayne Harrop is from Coventry University and specializes in systems and complexity with a deep training and virtual reality simulation background in emergency, security, resilience, communications, and cyber resilience concerns worldwide. And Lawrence Mitzall leads Whole Systems Approach, which is an operationally focused research and innovation practice he founded in 2022 after leading research and innovation projects for Serco's UK and Europe division over the last decade, where he translates research outputs into day-to-day operational needs on the ground. So we will then begin our discussion, but let me first ask Dr. Bucci to give his overview of the genome simulation. Anthony, over to you.
Chris, were we going to have Avi's opening remarks first?
Oh, I'm sorry, you're correct. Avi, I'm sorry, go ahead, Avi.
Hi, everyone. Actually, my real name is Anthony Bucci, so just take everything I say as an overview of genome. No, seriously speaking, good morning, everyone, or good whatever it is, depending on where you are. We're delighted that you've all joined us. We do think this is a very important and a very critical topic. You know, when you're dealing with approaches to deal with very extreme catastrophic hazards and events, it gives you pause, because normally the approach people have is they like to see good markets for whatever they're doing. They like to see examples of the need for whatever they're trying to move forward. That's a bit different here. We're not really very interested in seeing great examples out there of the need for returning from Armageddon and managing chaos. But we need to face it anyway. I'll try to be very brief, but I thought it would be good to help provide a sense for what the problem is that we are trying to face here. You know, everyone on the planet at this point has begun to realize that there is something new and different about our civilization. And if you've obviously seen what has happened with the interconnectivity with supply chain disruptions, these are absolutely unique historically. You know, there are babies who, if they could understand the problem, would understand very well their dependency worldwide on the closure of a factory somewhere in the United States. There are people who are now either close to starvation or starving because of Russia's invasion of Ukraine and the blockade that they're imposing on the Black Sea. And I think all of us have experienced supply chain delays, products, services that we need, we simply cannot get or can't get them on a timely basis. If this goes much, much further, which it certainly could, we'll have some deep problems. And fundamentally, why is this happening? And why is it global? Well, something became possible over the last really 10 to 20 years. The technology enhancements that we managed to pull together have been able to efficiently interknit and interconnect everything. You can't make energy anymore without finance. You can't do finance without healthcare products, without materials that come from all over the world. Everything depends on everything else. And when you have a very tightly interconnected system, in fact, if it's as tightly connected as ours, you need to begin to think of it as an organic system. Now, organic systems are great. Let's think about organic systems. Us, for example, animals, the great metaphor. The thing is, with an organic system, you have this very tight interconnectivity. If you disrupt an organ in an organism, it does not do very well unless it can quickly repair that organ. So what evolution has given to us and to organic systems is a systemic resilience capability, and it's called the immune system. There are really two choices as we look at the extraordinarily serious problems and really disasters on a scale that have not often been seen, all coming together these days in a perfect storm. If we look at the risks that suggests for the future, then we need to think through which option we would like to pursue. So the option that nature provides for developing a systemic resilience system is to kill off thousands or millions of generations and let it gradually develop. Read not generations in our case, but civilizations. That would not be a good thing. The alternative is to take the technology which made it possible for us to interknit ourselves so tightly together and find ways to use that technology to solve the problem by creating simulations of the whole complex interactive system that could make it possible to quickly understand problems and quickly find what could be the very complex but urgent routes to solve. What it comes down to is the experts you're about to hear from are the people who have their hands on the capability that may be very important for even human connectivity in the years and decades going forward. So the bar is quite high for our panelists, and I'm very much looking forward to hearing from all of them. With that, let's go forward and hear the real Anthony Bucci.
Thanks very much, Avi. And Anthony, please feel free to take it away.
Thanks, Avi. Let me share my screen real quick. Make sure this is working. Hi, everyone. Thanks for joining us today. I just wanted to go quickly through a few slides to give a very high-level overview of sort of our attempts to address some of these problems from the perspective of simulations. The types of problems that Avi alluded to are obviously intermingled with political, social, environmental, all sorts of different efforts and phenomena. But this is one particular way of looking at things that we're choosing for today. And I'll tell you a little bit about what we've been doing. So just briefly about myself, I have a background in mathematics and computer science. And specifically in computer science, I focused on what's called evolutionary computation, which sort of falls in the bigger umbrella of soft computing and complex adaptive systems. After my PhD, I spent about 6 years at a company called Ecosystem Corporation, which specialized in agent-based modeling. It was founded by a fellow from the Santa Fe Institute for Complex Systems in New Mexico in the US, with the notion of monetizing and making a business out of these ideas. And I did a few things in the meantime, but eventually joined EIS Council in August 2020 as a technical director leading up the genome effort. So I have a longstanding interest and background in simulation solutions to problems. So what is genome? And there's some word salad on this screen here, and I'll go through each of these points bit by bit, but this is kind of how we think of it. So, it's a large scale and network native simulation, meaning from the beginning, we've distributed the load across multiple servers, so it could be scaled out very widely, potentially as much compute resources as you're willing or able to supply, we could use to run a simulation. And that entails a bunch of things that we'll talk about in a minute about the coordination of such a thing. We like to think of it as an operating system of sorts. So it provides some facilities and things like time coordination being one of them that allow what we like to call infrastructure apps to interact in a shared simulated world. And by analogy, you can think of the operating systems you might be familiar with, like iOS or Android or Windows, as a metaphor. It deals in multiple sectors and their interconnectivity. So currently, this is a screenshot from an early genome version showing a number of different sectors. And you can see it's displayed on a map. This is the Louisville, Kentucky area. But you can see it's got a number of built-in apps already at varying levels of maturity. And it's an agent-based simulation. And by that, I mean that each of the entities you see, so each of the dots and circles on this screen, is an independent entity that has its own parameters, dynamic variables, it has its own behaviors, and has its own actions and effects on the world. So I want to just go through a couple key features of genome. Here's a screenshot of a growing version 2. But what you're seeing here is just a display of some data. So these are layers available as data in a version that we're building for the Haifa area in Israel. And as you can see, there's quite a lot of different entities being displayed. For some of those entities, particularly the power sector ones and the natural gas and electric emergency fuel sectors, we also have fairly detailed operating parameters of these different entities. So not just where they are on the map, but also factors that determine how they behave. Another thing that we represent and model is the supply chain relationships and the dynamic behavior that entails among the different entities. So you see here a kind of collage of screenshots from genome, but in the center, you'll see these blue lines, kind of a spider web looking thing. That's a representation of what entities depend on what other entities. So you select one entity and then you see these lines that display it's depending on services or resources from all the connected entities. And that is a fairly powerful feature in the sense that it allows us to simulate scenarios with a large scale kind of cascading infrastructure collapse, because these effects of one entity changing its behavior percolate through this supply chain network to potentially all the other entities and in varying complex ways through time. And I feel like this plus the agent-based modeling method make genome able to simulate things that have never happened in the world yet, but might. So this contrasts it with machine learning type approaches where you need data, particularly historical data, to train, and it's impossible to train a system on data about an event that has never occurred. So it kind of gives us the ability to explore things that could happen but haven't. Another key feature is that genome is able to functionally integrate third-party simulations. And what I mean by that is we have our own simulation of, say, electric grid entities, but a corporation that might have a simulation of their own infrastructure, or an electric grid operator that has a very detailed simulation of their systems, can integrate with genome, but only pass through to us high-level operational characteristics and not the low-level details of how those characteristics came to be. So they don't need to share with us private or sensitive or proprietary data in order to interact in a genome simulation, which is very key to expanding this. Not, there's a computational problem of how do you simulate at such a scale, but there's the sort of security problem of how do you incorporate simulations that have classified or secret or proprietary data they don't want to share with the rest of the world. And then finally, another key feature is that Genome is designed to function as a fully interactive digital twin. In other words, a representation of the real world, but in a computational space that takes not just simulated effects into account, but also real-time data feeds as those become available. Oh, I forgot the last one, which is really important. We do have a patent, in fact, on what's called an inverse interest management architecture that allows for quite a significant reduction in network traffic among the different components. Interest management without the inverse part is a well-studied topic, but our patent covers what we call an inverse interest management mechanism and architecture that, at least according to our prior art search, has not been explored very deeply, and in our experiments has shown quite a significant decrease in network bandwidth utilization, which is very important for distributed applications of this nature. So just to wrap up really quickly, where Genome is today, we have a prototype implementation for Louisville, Kentucky. You saw some screenshots from that. It has multiple layers and interesting effects can already be seen, but it has kind of notional data, not real operating characteristics of those entities, and a very rudimentary representation of electric grid operation. We're currently working on a higher fidelity demo for Haifa and Tel Aviv, and that involves some very complex scenarios, much more user control over the behavior of the entities. We have a load flow model for the electric grid now that also takes account of frequency deviations leading to potential failures in the grid. So that's a much higher fidelity model than we currently have in the Louisville, Kentucky prototype, and then some other higher fidelity model of natural gas and emergency fuel, and much more detailed GIS data and facility parameters, as you saw on the map. And then the things like federation and network coordination and the functional integration that I alluded to are sort of aspirational. We don't have those built and functioning today. I couldn't hook up your model to our model today if you asked me to, but those are in progress and definitely underway, and hopefully complete within the near term. So where we'd like to see Genome go, my last slide here, and this is a big old pile of words, but the notion is we like to think of Genome as potentially functioning like Waze for emergency managers, like a GPS unit that tells you how to navigate through traffic, but instead tuned to helping people who are dealing with a catastrophe see currently what's going on, so situational awareness, and then have some aids to help them make decisions about what to do in real time with what if scenario testing. Well, what if we did this? Would that help? Run a simulation and see. What if we did this other thing? Would that help? Run the simulation and see. Do this in the safe space of a computer before trying it in the world and potentially causing or not causing suffering. Yeah, so another potential application of Genome that we'd love to see it participate in is sort of ahead of time infrastructure planning. So by testing current vulnerabilities in a simulated system, we can make some educated guesses or suggestions about where to invest in order to increase resilience, for example. So we'd love to see a simulation play that kind of role. And then also training and exercising is another big area of application that we'd love to see Genome take part in. So that's it for me, just to kind of set the stage. And I guess I'll hand it back to you, Chris.
Thanks, Anthony. And I'd invite all of our panelists now to go ahead and open your cameras and your mics. And we'll get to the discussion portion. As they're doing that, let me just say that at EIS, we try never to be caught simply admiring the problem. So for the bulk of this discussion, we really want to try to hear thoughts from this fantastic panel on solutions that they've found to these types of challenges, the black sky chaos problems, or others that maybe aren't quite as big in scope. However, in order to do that, we do have to set the stage. It is important to define the key aspects of the scope and challenge. So what I first want to do is ask each of the panelists to lay out the challenge as they see it, the key topics that they focus on, and to try to include the scope, the systems and the populations that are affected in such a scenario. So I'll ask Saskia to begin, and then we'll go to Wayne, Lawrence, Anthony, and I may have a chip in myself, but over to you, Saskia.
Thank you, Chris. Yeah, hello everybody. I mean, I say rather good evening from Germany, and good morning to US actually. So yeah, so what my background is that I'm coming from the logistics industry, and we take majorly care of supply chain simulation. So we analyze when there's a production stop, what can a company do? If there's a certain risk involved, what can a company do? And then we find solutions, test them, as Anthony was also already mentioning, that simulation is quite valuable to test different scenarios, different options, and to see what is the best outcome in a certain situation. And the big challenge there with the supply chain is always the interconnectivity. So you have got several stages which are acting with each other and which are interconnected, and this strong dependency makes it very much unpredictable to forecast what is, if there's a change in the supply chain, what is the final outcome. So then I would hand over to Chris. Back to Chris.
Sure. I'll thank you very much for that. So the interconnectivity of the supply chain being the major challenge. So we're definitely going to come back to that theme. I'll ask Wayne for his overview.
Thank you, Chris. So hello from the United Kingdom. I work as an assistant professor at Coventry University, and I specialize in disaster and emergency management. Our research has looked at systems and complexity thinking in disasters and emergencies since the beginning of records. So we've started to look at a whole range of different types of disasters and emergencies across the world, particularly post-exercise, post-debrief reporting, and the sort of inquiries that occur from all over the world. Before that, I was a Category 1 responder in the UK, which is an emergency manager. And previous to that, I was in this sort of intelligence and security arena. So I understand some of the dynamic pressures within these environments. I think some of the biggest challenges are, quite frankly, the human component behind the system. The input is really important. And secondly, also just the sheer level of complexity of trying to scale up to a sort of meta model of understanding the problems. And that's not specific to any software. I think it's a challenge across the board. Thank you.
Thanks, Wayne. I think that's a good place to hand the baton to Lawrence. I could see him already nodding his head. So go ahead, Lawrence.
Yeah, no, thank you. And hello, everybody, also from the UK. I was recently with a large global company called Serco for about 16 years, leading their research and innovation programs across the UK and Europe. But Serco is a global company and operating critical infrastructure and services for governments and public sector agencies worldwide. And particularly many of those are mission critical: air defense, space, air traffic control, support to the various militaries around the world. And research and innovation, in my world, we saw it as a risk reduction exercise, because as Anthony and Chris and Wayne, Saskia have pointed out, the interconnectivity of the systems and the services that keep society going is critical. And if those break down, then the services that we provide, or Serco provide as a contract provider of critical services, become threatened. So simulation research and innovation, particularly on the human element and the decision making, as Wayne pointed out, regardless of the level of automation in a system, regardless of how remote some systems are operated, there will always be a human decision maker in the loop. And increasingly, as those humans in the loop become sort of less involved because automation, remote working takes place, their capacity and decision making needs to be improved. They need to understand better how to make better informed decisions, and simulation, particularly where the gaps in between the interfaces and interdependencies exist, and where those gaps exist are risks. And if you understand those risks and where resilience and risk and operational and jurisdictional and governance boundaries are perhaps not so resilient, and simulation can fantastically help with that, then those decision makers have a better ability to preempt, predict, and respond far better. And that's my interest, human in the loop.
Fantastic. Thank you, Lawrence. Anthony, some challenges or scoping the problem as you take a look at this from your point of view.
Yeah, so when I first picked up the work on genome, I went through this gruesome exercise of listing out different types of events like wildfires and floods and so on, and doing some basic research about what causes suffering in those events. And like in a flood, for example, I was a bit surprised to learn that drowning is the leading cause of death, but blunt force trauma in an automobile is the second leading cause of death, at least on average, for flooding, which means, car wrecks, basically. And the report I read didn't go into detail about how those car wrecks were occurring, but you might imagine it's during evacuation or just panic or what. So I feel like with particular events like that, they're fairly well studied. There's some data about this. You can decide, well, we're going to focus resources on helping people evacuate an area when a flood is coming to try to minimize the cause of death that we can control. But when we talk about black sky hazards, which is what we focus on in EIS Council, they don't harm people directly immediately. If the lights go out, if the entire grid goes down, it's unlikely to harm somebody except someone who's dependent on, say, a life support system. But the average person is unaffected immediately. However, it makes everything else at risk of collapsing, and then knock-on effects are what will cause the harm. So it's almost this kind of second order problem. And I would classify cyber attack in a similar kind of bucket. It's rare to see a cyber attack immediately. Nobody has perished, as far as I know, directly from the digital computer activity. It's from the after effects of that, right? So it's a different layer of risk, a different layer of problem that exacerbates all the other ones we already that we already understand, maybe not well enough, but to some extent. And so I see that it's a kind of risk that percolates then to everyone. Everyone, no matter what their social stature is or socioeconomic position, whatever that might be, potentially is impacted by these kind of hazards in one way or another. So that's kind of been my interest in looking into it. And as obviously with the rest of the panelists, I agree that simulation is a nice way to approach it, although there's lots of other interlocking pieces like political and so on that come into play as well.
Thanks, Anthony. I mean, those cascading, those secondary impacts, I think, are really important. So we're not at the point where we're dealing with Skynet and the computers and machines are just directly killing people, thankfully. But it is that those secondary effects. And I just wanted to add that what was brought out earlier is the importance of the simulation component, is this kind of having some pre-event ability to game out these complex interactions. Because just a short anecdote that was relayed to me during what was almost a black sky event in Puerto Rico after Hurricane Maria. Certainly the full-scale blackout and cascading infrastructure impacts check the box of our black sky definition. and it lasted for quite a long time. But it's just that it was contained on one island and wasn't wide enough spread. So there was an ability to respond. You can weigh in on how effective that response was, but to treat it in a more traditional emergency response framework of flowing help from the outside, evacuating people to the unaffected area, and so on. But one anecdote I heard was that a hospital in Puerto Rico realized they were short on supplies. They did have an emergency generator, and were needing hospital supplies. So first of all, they were able to contact people and say from the outside and say, well, this is what we need, but those supplies couldn't get to them because the port was damaged and there were supply chain backups at the port. When those were finally resolved, the medical supplies got to the hospital, but the hospital now was out of water. So the hospital wasn't running anyway. So now those supplies finally got to where they needed to be, but the supporting infrastructure couldn't, they were still useless. So you have all these knock-on cascading effects. So that's just kind of a real world anecdote we wanted, and why simulation is so important, because that's how you learn it the hard way. We don't want that to be the case. I see Lawrence's hand is up, so I'll pause and say and recognize him. Thanks, Lawrence.
Yeah, no, thanks. Just picking up on what you were just saying there, Chris, and Anthony, what you said earlier. And one of the things I always use in my projects, which I did at Serco, and we ran the UK's Emergency Planning College, still do for quite a while, and is a consequence-based approach to resilience. And it's very, the first thing that people look at in planning or responding to an event is the cause. Well, the cause is great, but actually, if you look at the consequences and you build those into your scenarios and your exercising and training, many events have a similar range of consequences. And a consequence-based approach to resilience and planning, preparedness and recovery, then actually you would find that an IED, for example, would have similar consequences as an earthquake in terms of urban search and rescue and the need to provide medical treatment and so on. So consequence-based planning in big black sky events could have a better approach.
Yeah, that's fantastic. It is one of the learnings that EIS had just basically as an organization was maturing, because we started out focusing on a specific threat. It wasn't IED. In this case, it was electromagnetic pulse. But what we soon realized is that's not the EMP isn't the issue. The issue is the power outage that causes it, and then the secondary cascading effects. And that power outage can be caused by a cyber attack or an earthquake or other things, not just not being focused on the threat, but like you said, being focused on the impact. Saskia.
I mean, that's exactly right. I mean, that's also a very important part once you start a simulation, once you construct your simulation model, because it's like there are quite a lot of different risks out there, but one has to have a look at the impact of the different risks. So then you can actually categorize the type of risk and then cluster them accordingly and integrate them into the simulation. And that's one of the major parts, because otherwise, you need to help yourself to handle the total amount of risks and to evaluate the different impact. So what Lawrence said is actually the complete right approach on how to deal and to set up the simulation model as well.
Well, let me follow up with you, because I was about to ask. I mean, you kind of teed up the question, and so as you look and how do you describe when you categorize and cluster these, either the threats or the outcomes or the challenges, and then look at how to strengthen in this case, let's focus on supply chains for a moment. So when you look at that, what kind of fixes do you find that have a protective or preventive effect for a number of challenges. And how can we apply those? Are those techniques applicable for this challenge, for a black sky large scale power outage?
Yeah, so you have got different risk categories, but most of the time, if you integrate them into a supply chain simulation, then they affect either the transport time or kind of a capacity at a certain production unit. So these ones are the major two impacts it always has got. It's mainly triggering down to, and then the effects, how to deal with that, they are quite, there's a big range, because then you have to have a look at the complete supply chain setting. There are options, for example, now if we have a look at COVID-19, so we had always the production closure, we had like a disruption of container exchange flows, and we had like the big issue about the parts availability. So here, the companies mainly first had to look out how can they transport differently. So in between, they also took flights to bridge the shortage in transport. And then you have the capacity, the capacity shortage, which then triggered a parts non-availability. And here companies actually looked out for different suppliers, mainly then also back in Europe. So a lot of suppliers which came from Asia, they were actually blocked during COVID-19. So one looked out for European suppliers in the case of a European producer. Then it was like difficult to change. I mean, all this change had to be evaluated, had to be integrated also into the complete supply chain setting, and to fix the lead times, which kind of rhythm should the supply be taking, so at which kind of frequency the supply should be given to the production unit, so that it's fits into the complete overall setting of the supply chain.
Thank you. Wow, that just there's so many threads there I want to follow. This is the best panel ever because they're just hosting it for me. I'll go to Lawrence. I'm sorry. I'll go to Wayne. He had his hand up first, and then to you, Lawrence, in a second. Go ahead, Wayne.
Thanks, Chris. I just wanted to add a little bit of reality to the types of challenges that we're facing. So in 1990, I think it was 8, Stern and Feinberg did a study of nuclear safety in the US, and the report was published, and they looked at the thing called risk characterization, because Saskia's talked about risk, and they identified that risk must have a characterization of risk, which is different depending on who does that risk assessment because of the subjective nature of it, has to include good discourse, so strong, vigorous discourse and challenge, and also very detailed analytics and information that supports that. So to come up with a high, medium, or low risk really depends upon good discourse and good, strong analysis. I'm not so sure that boardrooms have that in every case, which then poses a problem about disconnect between the real problem and the risk perception or the perceived problem of the risk. That in itself affects the planning cycle. So I'd say that outside of any system or technology, we need to fix the human perceptual issues around this, the human factors, situational awareness, decision-making characteristics. We can look at lots and lots of even small type disasters like Columbia and Challenger. We see inherently problems in the thinking and faulty rationalizations that occurred that led to those problems. There's no reason to believe that on a grand event, a maximum event, that we won't see even more of those challenges. Final thing I'll say is this, is that you can't use scientific reductionism to understand a complex system. Scientific reductionism posits that you can break something down to its smaller parts and understand it. No. That's an absolute fallacy in the world of systems and complexity thinking, where all the research has been done on it. We're looking at the properties combined properties that a system produces. So for example, a car has a spark plug and that spark plug ignites, but the spark plug in itself doesn't make the car go forward. It's a combined property of all of the other features of the car. So we have to understand the input and output of properties through a system and not the system itself. It's a huge difference.
I'm going to come back and ask Anthony to opine on the complexity piece, because I know that's part of what his real interest is in these kinds of problems are sort of like emergent behavior, and so that's a really interesting component. But I want to say just a quick reaction to Wayne's point. We don't want to. You have to end the discussion at some point and make a decision and make a risk determination, but it does seem to point to a best practice being that you want a pretty wide and diverse group of folks that are giving those subjective inputs, because if you have too many people that are all the same in that same boardroom with the same backgrounds, they're going to miss pieces of the risk landscape. I would imagine. Is that something that you wanted to were you were driving, Wayne?
Kind of, right. So there's a concept called conceptual slack, and conceptual slack is the degrees of different perspectives on a problem. And so if you have too many different variant perspectives, you can get conflict in the boardroom or anywhere else, and it becomes paralytic in that sense. So it adds to the problem if you have too many different perspectives, but at the same time, if you have one single dominant perspective, you don't get a reality. So this is always a fine balance between getting the right perspective, and humans are fickle. This is the way we operate. We often operate not on the data, but on our gut feeling. And so that can aid us in some cases, because I've worked in emergencies in frontline where my intuition has served me well and it's helped, even though the data was at discord with that. But at the same time, it's a real knife edge. There's lots of things, complexity, this element of tight coupling, and the issue of things like the uncertainty in the system are really important. Let me just add one final thought. The more layers of redundancy, that means capabilities to manage the problem, you add to a complex system, the more you make the system more complex.
Exactly. So we're looking at sort of a Goldilocks point where we do the proper, where we have the proper risk perspective. Lawrence, go ahead.
Yeah, I mean, just picking up on Wayne's point there. One of the issues where you have multiple stakeholders from different organizations, different disciplines, who need to collectively work together, whether it's in a supply chain, whether it's in emergency management, whether it's in planning and preparedness, is mostly those people approach whatever the challenge is from their own perspective of risk. When they approach that perspective of risk, driven by their experience, driven by their the organization that they're in and the structure that they work within, then drives policy, governance, budgets, training, and so on. So when that collective group of stakeholders need to be interoperable to achieve a set of shared outcomes, so in the case of a consequence-based approach to emergency management, let's say in a system, then being don't mean will this plug fit into this hole, into this socket. I'm talking about interoperability at a governance, to policy, at a decision-making level becomes very, very difficult. So one of the things we try and do when we're creating scenarios is to get all of those different stakeholders, different actors from their different perspectives to step back. And the first thing is to agree their shared collective understanding of risk. And then you walk forward. And as you walk forward collectively, ticking off, moving forward, reach that set of shared outcomes, and then a shared risk register from which each organization, which each individual can then adapt their own local risk registers based around the collective challenges. And you know, as Wayne said, humans are fickle, and you need to get the combined effect of the collective effort sorted. Too much becomes more complex. Too few, it becomes very, very focused, very linear, and very introspective.
So good point. So a a certain breadth of perspective, but there has to be a commonality of language and framework, or you can't really have a discussion. You'll be talking past each other. Saskia,
arguing over risk.
exactly.
I mean, sorry, just one example. I did a nuclear risk workshop, and I had 40 experts, and there were 40 different perspectives and views on risk. So,
right. So that's the paralysis by analysis type of
exactly.
situation. We have to avoid that. And Saskia, I'm interested to hear if that's the direction you're going, but please go ahead.
Yes, it's exactly that's what I wanted to pick up now also. So if we have got so many different perspectives, we need to have somehow transparency. And then I would to pick up this the point which Avi was mentioning in the beginning. So he mentioned actually that we need to have we have the advantage of technology, and this advantage we actually need to use. And once we involve technology, we can actually make transactions and risks transparent within the different infrastructures, and provide then also a decision base for the human beings, which kind of risk factor is has to be evaluated in which manner. And then you couple that again with the simulation tool, and you will see then the effects once you take a decision in this way or that way. And then you have got an option how to decide and how to develop or to deal with the type of risk. So that's an important point. That's what also Wayne mentioned, actually, this transparency with technology, and then you can couple that with the human being, or with the people, the staff, which you have integrated, the people who have to talk to each other. Also, that was one point which Wayne was mentioning. It's like all about talking to each other and saying, okay, I'm doing this one decision, or I make it transparent via technology to say, okay, I've taken this one decision, and accordingly the other partners connect. Thank you.
Thank you. I guess I will just go ahead and ask Wayne to respond, because I think that was a great point, and I think that it's interesting to think of it as the technology enabling the discussion and enabling transparency, because I think a lot of people think of it sometimes, well, this is a black box. I put in some input, it spits out an answer that tells me what my risk score is, and it's mysterious. But what you're saying is, in fact, you need to do it in a way that shows everyone this is how we're taking into account and weighing these factors, and so everyone can really actually understand that it can actually be a way to speak to each other more effectively. Wayne.
Thanks. So most emergencies, crises, disasters, catastrophes, whatever you want to use as a synonym, have elements of emergent property. They create and do things that no one anticipated. And we don't have the power of the deity to understand all of the dynamics. I'd argue that the more complex, interconnected, the more tightly coupled, and the more expansive a system is, the more chances are that you're likely to find emergent properties. Things pop up that you just didn't anticipate. So that's the first thing, and no human can recreate every potential vulnerability. Systems have got the potential to do some head work on that and help us, but not definitively, because when AI systems speak to AI systems, you get problems immediately. So I'll give you an example of one provider. So one provider, Wikipedia, which we should all know, had released botnets that would go around and tidy up its information, and then other botnets came around and tidied up the information that the first botnet had produced. So you ended up with constant shifts in the text as a result of sort of these different conflicts between the system. So there are properties between AI and AI that need to be worked out. Between human to AI, any sort of crisis has a human input in it, and we call that, well, in 1978, Barry Turner produced this term, and he was a prolific researcher, produced this term called socio-technical disasters, because there's a human input as well as a technical input. And if you think about it, something like the Challenger and Columbia disasters, in one of those scenarios, the O-ring didn't expand sufficiently, and the information was known about that from Morton Tycho that reported it, but it was overlooked because of pressure under the system to respond and launch the craft. So we're dealing with human dynamics. Even if the data purports to say something, people will very often disavow, distort, or undermine the information to fit the picture that they think is correct and they strongly hold. So we've got to deal with all of those dynamics in the way that people operate. In 1984, a good book to get hold of is Charles Perrow's book, Normal Accident Theory. And normal accident theory posits that disasters in complex systems, which is what we're talking about, metagrid, are inevitable. They will always happen. So whilst we can chart them and try to understand them, and that's a good step forward, they will always happen, which is actually good business for genome and everything else, right? Because it's always going to be there. But at the end of the day, there's also a piece of research done on high reliability organizations by Berkeley researchers that looked at 5 characteristics that make systems more resilient. So I'm not going to go through it all because I haven't got the time, but there's some pieces of information there to go and research in this field. It's been studied since the 1970s. There's nothing new substantially to the argument that we're having here.
Nothing at all. Nothing new.
Chris, you're on mute.
I'm sorry, I got too excited. I wanted to actually pivot to you, Anthony, because I think Wayne raises some excellent points here, and I know that the emerging the complexity, emerging behavior, the tight coupling are things that you're trying to ensure that these are things that we're trying to capture, because other models that are siloed are going to miss those kinds of things. And so in the service of building resilience. So I wanted you to respond, and I saw it seemed like you wanted to jump in. I saw your hand go up anyway, so go ahead.
Yeah, I guess before diving into that bit, I kind of wanted to comment that the conversation among Wayne, Lawrence, and Saskia reminded me quite a bit of the book, The Wisdom of Crowds, and particularly the failures of, when can a crowd fail to produce a good outcome. And, he posited things like homogeneity when there's not enough diversity of opinion. I don't recall that he talked much about what Wayne pointed out, that there's this paralysis if there's too many opinions, but definitely having homogeneity is a problem. And he talked about centralization, where the hierarchy sort of dominates and individuals don't have enough of a say, which relates. And then sort of division, where there's not enough transparency or sharing of information, which Saskia pointed to, and imitation, and I guess emotional response as well. So there's a lot there that I think, and again, to Wayne's point, that book was written a long time ago. So this research has, and obviously been built upon quite a bit since then. So this research has been around. But I guess my own sort of interest, being a computer scientist and coming from a background in math, is I like to think, obviously all the human factors are extremely important and not to be ignored. But I think one of the things we've learned from complex system theories over the last few decades is that there are sort of common themes and common things that can happen that are abstract to many kinds of complex systems, and nevertheless appear in these very grounded ones. And the one that always pops into my head is what's called the percolation threshold, which is this notion that, imagine you have like a soil layer, and you're wondering whether the water can make it from the top to the lower part of it. And the fraction of empty space in the soil has a very huge impact on whether or not the water can make it. And there's a very severe phase transition. So if it's 10% holes, no, probably not. 20% holes, probably not. And then somewhere around, whatever, it depends on the system, obviously, but let's say around 50%, it'll go from most of the water won't make it to all the water will make it in a very short change. So you can go from 51% holes to 52% holes and see the difference between no water makes it to all the water makes it very rapidly, right? And it has to do very much with how you interconnect things in a complex network as well. If you have the natural gas, emergency fuel, and electric sectors kind of depending on each other to some extent, issues may not percolate from one to the other very much. But there's a certain level, there's a critical level of connectivity where once you hit that, then one small problem in one place could easily percolate through the entire system. And that's an abstract concept, right? You can model that without even talking much about the details of the physics or any of the people involved. And no matter how good the personnel are, they may not be able to stop such a thing from happening because that's just a basic feature of a system like that. So that's kind of like where I like to come from when thinking about these sorts of problems, in addition to the other ways to come at it. And one thing we'd like to, I couldn't say I can see that in Genome, but I do know that someday we will probably be able to model stuff like that in Genome. And I know it's been studied in the past that particularly with the electric grid, the interconnectivity among the different components does have that kind of property already. And as we roll more and more things to become dependent on electricity, I would cite electric cars being an example, the movement away from physical labor to gas-powered labor to then electrical mediated labor. There's a big push to do that. And that's been going on for quite some time, but the more dependencies we introduce on the electric grid that already has this property, the more we're introducing the possibility of this kind of percolation problem through the other systems as well. And to the extent that they also influence the electric grid, we've added a feedback loop that then affects the electric grid even worse. So that's kind of like, that's a lot less grounded and concrete as some of the things that Wayne was saying, but I think it's another aspect to bringing simulations to the table is that we can look at from that perspective as well, that take a step back and see these kind of big system properties too, that would be very difficult to see using a reductionist method, let's say, as Wayne alluded to early on.
Right, good point, Anthony. I wanted to, let me frame it. We're coming up to the top of the hour already. I mean, it seems like we just started talking, so it's, but a random member of our audience named Avi asked a good question that I wanted to kind of frame maybe our final question on, but I think it's along the lines of what we were just talking about in a way, but is the importance of simulation, because there are these threshold effects, strongly nonlinear effects that emerge, and using these simulations, but also Avi's question had to do with whether insurance companies might need to start using this, because using sort of traditional actuarial risk, where we just have a big data set, you say, well, I look at it, it happens 17% of the time, so that's the risk. I don't think that works anymore in these types of complex systems. We have a changing environment, so if we're talking about just environmental data, that's all garbage in, garbage out. And so if the data set isn't any good anymore, these types of interactions and best guesses and risk analysis and all of those components are going to have to be, I think, where how risk is calculated. And then if that's the case, I mean, I think that the insurance sector can have a huge positive impact, as they have in certainly driving behavior through incentives. So this is kind of that's a hell of a last question to give everybody, but we got the people to do it. So I'll start with Lawrence.
Actually, I wasn't going to make a point about the insurance, but as it's come up, there is a way to bring insurers to the table, and some insurers and brokers.
I think we got a pause on Lawrence. Go ahead, Lawrence. You froze for a second, but go ahead.
Okay.
Maybe back up 10 seconds and go.
Yeah. So there is a way to bring them to the table, and they have huge research departments, and that focus of those research departments is to mitigate risk and keep their payouts down. So if you take a company like Serco that operates critical systems and services, satellites, for example, when those companies, it's not just Serco, there's lots of companies that do it, when they win those contracts, they have to have insurance. They have to insure the contract, one. If they cannot insure the contract, their ability to fund those contracts, raise finance to run those contracts 10, 15, 20 years becomes very expensive, if not impossible. So the ability to demonstrate how this approach, simulation, risk mitigation and reduction through understanding of the system, which is my second point, you can bring those insurers to the table to demonstrate how you're mitigating the risk and therefore how you're reducing the likelihood of those contracts being affected, and therefore business continuity, reduction in payouts. So it has to be client led to the insurers. That's the first point. And then on the second, system, which might be helpful, everybody always asks, what's the system? Well, you know, you take a piece of infrastructure and you draw a circle around it. Well, no, you don't. So one of the things that we use, which is really helpful, is there are always 6 capability areas, 6 capability domains that underpin any one single organization or multiple organizations operating within an ecosystem: governance, people, process, technology, information, and infrastructure. Those 6 pillars, capabilities, are interdependent and interfaces. And it's a bit like defense lines of development, where you have to understand what's supporting and what's being supported. And if you focus on those 6 areas, and then you have your resilience boundaries, a risk boundary, a resilience boundary, an operational boundary, a jurisdictional boundary, a legislative boundary, where you know, governance changes, policy changes, operational control changes. When you have one of those boundaries, that's a risk. It's not resilient. Where you understand where you have multiple boundaries which can mutually support, then it becomes resilient.
Fantastic. Thank you. Yeah, that's wonderful. So there is a kind of analysis that can be applied to this, and so those are the kind of solutions that we're looking at those 6 areas, et cetera. Thank you very much, Lawrence. Wayne?
Yeah, just on the insurance side. So insurance can be useful. For example, it has catastrophe modeling data, probably not up to the scale that we'd need to ramp up for metagrid type issues, but it certainly does have some data and its actuary systems. But the insurance company is not stupid either. They're going to insure things on a case-by-case basis. So business interruption insurance or building terrorism insurance or whatever. So they're going to segment their insurance policies to reflect specific areas of interest. In addition to that, some areas will be uninsurable. You simply won't be able to get insurance for that. If you live in a consistent floodplain or something like that, you don't get insurance in the US and other parts of the world. And of course, there's the magic thing called force majeure, which means that they get out of those deals. The other thing that I wanted to say is that planning is useful, and the system, Genome and others, will provide planning frameworks and coordination, subsidiarity, and all of the other things that come with it. That's useful, but the specific data points may not be useful or only for a given point of time, because if you look at Google Maps, it's not the way that the city is now, it's the way it was when they mapped the city. So with that in mind, Google Maps has system atrophy. It loses a degree of reality and disconnect. So in the same way, the infrastructure system is constantly going through regeneration, change, transformation, and the data points that you have need to reflect that to be up to date. And that is a mammoth task. So just be careful. And the final point is, don't underestimate the political persuasion in this. We've all been through a pandemic and we saw that there wasn't really solid plans. The politicians had to make up what to do in the process. So in some areas, we have such emergent trend of risk and no policy or full structure to manage that. And so how you replicate areas that are deficit in terms of national planning policy would be an interesting element, because if you're talking about metagrid failure, you're talking about the worst of the worst. That's why I call it black sky.
Thank you, Wayne. It reminds me of a colleague of ours likes to say that any individual plan may not be that important, but planning is very important. So thank you for that. Saskia.
I think, I mean, the insurance companies will definitely be able to learn out of this, out of the data which they can actually now apply out of the new technology which they can use, and they can further and more easier now predict in which kind of areas they have to allocate money or put aside some money because they expect some risk is going to happen. So in that regard, I mean, they can actually, first of all, understand risk earlier. They identify risks in a quicker manner, and they can somehow also forecast risk, and then also warn companies or take it as kind of a warning system, but also for their own calculations to know how much money they have to put in which kind of area. But naturally, I mean, it's right, in some areas you can't get an insurance. It's just if there's a constant flood, I mean, let's try to avoid that these floods are happening more frequently, that there are any hurricanes happening. So we have to do a bit on our end to ensure that life is staying as it is.
Yes, good point. Good point. Anthony, any final thoughts?
Yes, if you'd indulge an anecdote for a couple of minutes, I know we're over time, but when I worked at Ecosystem, which is a company I mentioned that we built agent-based models, we had a project with a large health insurance company where they had introduced one of these programs that allows you to reduce your monthly premium if you have a gym membership, for example. So it was a bit more complex than that, but that was the basic idea. And what they observed when they introduced this program, they had the program and then they made some changes to the structure of it that they thought would enhance utilization. And what they found was the opposite happened. People stopped using this program. And so they contacted us because they had no idea why that was, and they were wondering whether our techniques could help them understand that. So I did not build this model, but one of my colleagues built the model, and we talked a bunch about it internally, because what had happened, it seems, is that the rules had this unanticipated consequence that people would see whether or not they were about to reach a milestone that would allow them to have a policy reduction, and then basically be like, I'm never going to reach that, I give up and stop. And so you saw this, if you sort of plotted a plot of people's progress towards the milestone, there was this kind of pile-up effect where right towards the milestone there were lots of people sort of there and then hopping it, but then there was this kind of trough of a trough region where people were kind of giving up, and then back behind that a bunch of other people in that state who are maybe still trying. So I think it's an interesting cautionary tale that what seems to be a nice and plausible mitigation or program could have some very counterintuitive, and in some cases the opposite effect of what you were trying to achieve. If you just, it sounds plausible, everybody in the room was an insurance person, I'm sure they modeled it with their actuarial models and so on, and it made all kinds of sense. But in the real world with human beings and such, who can see things that maybe you didn't consider in your modeling, it could have the opposite effect. It could actually have a bad effect, right? So I think I'll just leave it there. You can take from that anecdote what you will, but the simulation we built was able to expose that effect given enough time that hadn't been seen prior.
I'll try to summarize that as choose your incentives carefully. Thank you, all of you. I need to wrap up, and of course, we're into overtime, and it's because this was such an amazing and interesting discussion, and I'm sure we could continue this for another hour easily. So I appreciate everyone's wonderful insights and participation. Let me just give you our outro information here. We have a couple of upcoming events. If you enjoyed this one, in 2 weeks' time, we are hosting a sort of a virtual tabletop exercise, cyber and electromagnetic pulse strike. A global panel of experts will be playing in that virtual tabletop exercise. You can find information on that on our website. One of those threats, not the cyber, but electromagnetic pulse, is a handbook that EIS Council has put out. That handbook, along with all of our materials, are available for free to our members, and membership itself in the EIS Council is free through the end of this month. At beginning of July, we are going to begin charging a still very reasonable $100 a year fee. But if you're enjoyed this and want to have access to our library, please navigate to our website and join EIS Council. So eiscouncil.org. You can also shoot us an email. Please let others know if you enjoyed this or other discussions and want to participate. Please share info about EIS Council far and wide. We appreciated everyone, all the panelists who joined us, but also the robust discussion that we had in the chat with all the other attendees. So thank you very much, and I'll give you back the rest of your day. Thanks so much, and take care.